Let's pick up from where we left off in our last video lesson. We imagined a hypothetical case. What if you could drop something through a tunnel that goes to the other side of the Earth? If the center of the Earth represents an equilibrium position, then the question is, starting from here, let's say we drop the object in from this side. At that point, x initial is just equal to capital R, the radius of the Earth. And so we guessed that the position as a function of time would be equal to R times cosine omega t. So this quantity omega we found must be equal to the square root of gm divided by r cubed. And we called that the angular frequency. And we also found that the period would then be 2 pi times the square root of r cubed over gm. And that's where things got interesting, because we can easily see that's the exact same expression for the period of a satellite in a circular orbit. So, in this video lesson, I just want to make sure we're clear on these different symbols, omega, f, and t. These are important symbols in our study of periodic motion. Whether we're investigating an object that's attached to a spring and vibrating back and forth in simple harmonic motion, or we're looking at the behavior of a simple pendulum that swings to and fro, the period is nothing more than the amount of time it takes to complete one vibration or one oscillation or one cycle, however you want to say it. Okay, all the same thing. F stands for frequency. You might say, wait a minute, I thought that's what omega stood for. Well, there's two different types of frequency. There's frequency and there's angular frequency. Capital T is period, and the units are seconds. Lowercase f is frequency, and the units are cycles per second. Now, 1 cycle per second has a nickname. It's called a hertz. Omega is angular frequency, and its units aren't cycles per second, but rather radians per second. And there's no special nickname to that. A radian per second is just called a radian per second. But we know that for every cycle, there are 2 pi radians. And so there's a relationship between angular frequency and traditional frequency. And that's really simple. Angular frequency is just 2 pi multiplied by typical frequency. Okay, so we can at least relate these. If you know one, you know the other. The other way to write this would be frequency in hertz is equal to angular frequency in radians per second divided by 2 pi. I'm just rewriting the equation inverted. But what about the relationship between period and frequency? Well, that's an inverse relationship. Actually, it's not just inversely related. They're true inverses of one another. Period and frequency aren't just inversely related, they are true inverse quantities, meaning period is just equal to 1 over frequency and vice versa. Frequency is equal to the inverse of period. Think of it like this: if you blink as fast as you can, some people can blink 15 blinks in 3 seconds. So that would correspond to 5 blinks per second. And we can think of a blink as your eyelid going down and coming back up. In other words, each blink represents a cycle of motion for the eyelid. So what value did I give, the period or the frequency? Right. Turns out we've directly calculated the frequency is 5 hertz. If a person who blinked in this manner said, "I'll be back in the blink of an eye," which is an idiom we often use, if you take people literally, then you would assume that this person would be back in a time of 1/5, which would give 0.2 seconds. So a person who can blink 15 times in 3 seconds blinks with a period of 0.2 seconds. Frequency and period are true inverse of one another, and angular frequency and regular frequency differ by a factor of 2 pi. So keep that in mind as we progress through this unit of study. We're going to see the symbols T, F, and omega repeatedly.